Usually, when we talk about computer memory, there is this expectation of, like, absolute literalism.
Oh, yeah, completely.
Right, like we treat it like a physical storage locker. You put a digital file into the locker, you shut the door, and when you open it back up, you expect to retrieve exactly what you put in, like a perfect bit-for-bit, pristine recreation.
Yeah, and for decades, that binary expectation was basically the only way to build computational systems. I mean, the data is either perfectly intact or it's corrupted. There was really no middle ground.
Right.
But when you step into the world of large language models, and specifically how they remember the context of an ongoing conversation, that whole storage locker metaphor just fundamentally shatters. We're looking at a landscape that is no longer about storing static files.
Which brings us to the core mission of our deep dive today.
Hmm.
We are looking at a massive stack of sources for you today. We've got deeply technical documentation, hardware architecture designs, and some really incredible scaling law experiments from the Shannon Prime project.
Yeah, the Shannon Prime stuff is fascinating.
It really is. And our goal here is to completely dismantle how you think about AI memory. We are looking at this massive memory bottleneck, known as the key value cache, or KV cache, and exploring how it's just being radically re-engineered. As the sources show, this isn't just about, compressing data so it takes up less space.
No, not at all.
It's about treating AI context as a mathematical signal rather than a physical object.
Right. And the sheer scale of the problem this solves is what makes the underlying math so critical. By the end of this deep dive, you are going to understand how it has become mathematically possible for an AI to fit a 50,000 token context window, which is roughly the length of a short novel, on a standard off-the-shelf smartphone.
Which is just nuts to think about.
It is. And to do it without melting the battery or, crashing the operating system. And the most incredible part of this architecture is that it relies on mathematical theories about multiplicative lattices. It uses the way prime numbers organize data to shrink gigabytes of storage down to megabytes.
Wow. Okay, so before we can talk about storing data efficiently on a phone, we really have to understand the fundamental nature of the data we're actually trying to store.
Exactly. You have to look at what's under the hood.
Right. So in a standard large language model, for every single word or token the model processes, it generates two crucial mathematical representations. You have a key vector, a k, and a value vector, a v.
Right.
And it has to cache, or remember all of them, to maintain the context of a conversation. The longer the conversation, the bigger the cache. And the industry's reflex up to this point has been to just squeeze that cache, right?
Yeah, just dropping bits to make it smaller.
Exactly, dropping bits while basically treating the k vectors and the v vectors as if they were identical types of information.
And treating them identically is, it's the fundamental flaw in early AI memory management. I mean, a major discovery in the Shannon Prime source material is that key vectors and value vectors possess completely distinct mathematical topologies.
All right, they're not the same beast at all.
Not even close. They behave entirely differently when subjected to a specific mathematical filter called the Vilenkin-Hartley transform, or VHT2. But to understand why, we kind of have to look at how these vectors are forged in the first place.
Okay, let's unpack that.
So k-vectors are primarily responsible for encoding spatial position. They basically tell the attention mechanism where a token is located relative to other tokens in a sequence. Modern transformer architectures accomplish this using rotary position embeddings, or ROPE.
ROPE is such a fascinating mechanism because instead of just attaching a static number to a word to indicate its position, ROPE takes the word's embedding, its coordinate in high-dimensional space, and applies an actual mathematical rotation to it.
Yes, exactly.
The angle of that rotation corresponds directly to its position in the sentence. It's like taking a compass needle and rotating it a few degrees further for every subsequent word.
That's a great way to picture it. And because of these deterministic rotations, the k-vectors end up carrying a highly structured, highly predictable geometric pattern.
Right, so it's very orderly.
Very. And when you take that geometrically structured k-vector and you run it through that VHT2 transform, you observe this massive phenomenon, signal concentration.
Okay, signal concentration, what does that actually look like?
Well, the VHT2 essentially acts as a prism, right? It breaks the vector down into its constituent mathematical frequencies. Because of the predictable angular nature of the ROPE encodings, more than 80% of a k-vector's energy concentrates in just the first 20% of its spectral bands.
Wait, 80% of the energy in the first 20% of the bands?
Exactly. The vast majority of the spatial information lives in that extreme low-frequency domain.
Wow, so that is an incredibly dense concentration. It basically means the data is highly ordered. But if we run the value vectors, the v vectors, through that exact same Blankenharley prism, the result is entirely different, right?
It is entirely different. The energy of the V vectors spreads uniformly across all the frequency bands. It looks completely flat. I mean, it's virtually indistinguishable from pure random noise.
And why is that? Why is it so flat compared to the k vector?
They lack that concentration because of what they actually represent. While K vectors encode the structural position, V vectors carry the semantic content. They hold the actual meaning of the tokens, the definitions, the nuanced associations, basically the messy reality of human language.
Ah, okay. And language is messy.
Very. Language is inherently high entropy. It is unpredictable. Therefore, the mathematical representation of that language, the V vector, has to distribute its energy evenly across the entire spectrum to capture all of those chaotic, high-frequency semantic details.
You know, a great way to visualize this profound asymmetry, this difference between K and V, is to think of the difference between a topographical map and the actual physical terrain it represents.
Ooh, I like that analogy.
Right. So the K vector is the coordinate map. It's highly ordered, sparse, and structured by this rigid mathematical grid. You can compress a map incredibly efficiently because a massive portion of it consists of predictable contour lines and, empty white space. But the V vector, however, is the terrain itself. It's the dense forests, the jagged rocks, the mud, the scattered leaves. It contains all the complex high-entropy reality. You just cannot compress a high-resolution photograph of a forest the way you compress a line drawing of Memorap without, blurring the actual trees into a green smudge.
That is exactly right. And recognizing this map versus terrain asymmetry is the key to extreme data compression. Because treating all data uniformly wastes immense resources.
Right, because you're treating the map and the terrain the same way.
Precisely. If you allocate an equal number of storage bits across the entire spectrum of a K vector, you are wasting memory on the high-frequency bands that contain almost zero actual energy. But by mapping the specific concentration of the K vector signal, developers can allocate memory bits strictly where the structural information resides.
So they give high precision to that first 20% of the bands.
Exactly, and effectively ignore the empty noise tail at the end.
Okay, so this all sounds perfect in theory. The map is predictable, so we compress the map. But looking through the Shannon Prime hardware experiments, there is this massive paradox here.
The fragility issue.
Yes. If the K vector is so perfectly structured, why is it that when engineers aggressively compress it, the entire AI model sometimes just collapses? I mean, the sources clearly document that dropping the wrong bits on a K vector causes the language model to suddenly output complete gibberish. If it's just a map, why is the AI so fragile when the map loses a little resolution?
Well, answering that requires us to look at the literal physics of how errors propagate inside a neural network. And the researchers didn't rely on intuition here. They derived an empirical scaling law.
And the scaling law is crucial, right?
Absolutely. It mathematically defines how errors in the reconstructed KV cache translate into downstream perplexity. And perplexity is just the standard metric for measuring the degradation of a language model's predictive accuracy. The equation they discovered maps this relationship precisely.
Let's actually look at the math here, because this equation really dictates the entire physical architecture we'll discuss later. So the scaling law states that the degradation in the model's performance and the change in perplexity is proportional to a specific fraction.
Right.
The numerator is the error in the K vector squared. Then you divide that by the denominator, which is the number of parameters in the model to the power of 1.1, multiplied by the precision of the model's weights in bits to the power of 1.5.
Yes, exactly.
So to spell out, delta PPL over PPL is proportional to 1 minus K correlation squared over params to the 1.1 times bits to the 1.5. I want to tackle the top of that fraction first. The numerator explicitly shows that the error in the K vector scales quadratically. The exponent is a 2.
And that quadratic exponent is the direct mathematical consequence of how the attention mechanism actually operates. Transformer attention is fundamentally a bilinear operation.
Bilinear meaning it involves multiplying two things together.
Exactly. To determine which previous words are relevant to the current word, the model takes a query vector and calculates its dot product with the key vectors in the cache. It multiplies them. Because the attention score relies on this multiplication, small angular errors introduced by compressing the key vectors do not simply add up linearly.
They compound.
They compound quadratically. Furthermore, those multiplied scores are then passed through a softmax function, which uses Euler's number to exponentially magnify the differences between values.
Wow, okay.
So it turns small angular deviations into massive misallocations of attention.
It's basically the mathematics of a ship's navigation. If you are captaining a ship across the ocean and your initial bearing your query is off by just 1 degree, and the grid lines on your compressed navigational map, your key, are warped by another 1 degree, those errors don't safely add up to a manageable 2 degrees.
No, they don't.
They multiply against each other over the vast distance of the mathematical journey. By the time you reach the other side of the attention mechanism, you aren't just slightly off course. You are on the wrong continent entirely.
That is a perfect analogy. That quadratic compounding is exactly why compressing the spatial map is so incredibly dangerous. A single percentage point of error introduced into the k-vector can cost a model as much accuracy as a 10% error in the v-vector.
That's wild.
The entire calculation relies on absolute angular precision. However, the denominator of the scaling law reveals the mechanisms that counteract this fragility. The first variable in the denominator is the parameter count of the model raised to the power of 1.1.
So params 1.1.
Right. This indicates a slightly superlinear relationship between the sheer scale of the neural network and its ability to absorb compression errors.
Wait, so as the physical size of the AI model grows, its tolerance for a corrupted k-vector actually increases, which feels completely counterintuitive until you look at the internal architecture of a massive model. Because a behemoth like the Llama 70 billion parameter model possesses vastly more attention heads than a smaller model, right?
Exactly. It has an enormous number of attention heads running in parallel, calculating hundreds of distinct geometric relationships simultaneously. And when you do that, you trigger a statistical phenomenon.
The averaging effect.
Right. The uncorrelated reconstruction errors generated by compressing the k-vectors begin to average out across the crowd of attention heads. It is essentially a massive mathematical jury where the random mistakes of individual jurors cancel each other out, preserving the integrity of the final verdict.
And the scaling law experiments provide stark empirical evidence of this averaging effect. I mean, to maintain high-quality language generation, a massive 70 billion parameter model can safely tolerate a k-correlation floor, meaning the accuracy of the reconstructed k-vector compared to the pristine original of just 0.927.
Yeah, so the cache can actually be quite lossy in a big model.
Right. But by stark contrast, a tiny model like the Dolphin 1 billion parameter architecture lacks that massive parallel jury. It requires a strict 0.9888 correlation.
It demands near-perfect reconstruction.
Because it simply doesn't have the spare attention heads to absorb and average out the mathematical noise. So the larger the model, the more forgiving the math, allowing for vastly more aggressive compression.
And we cannot ignore the final variable in the denominator of that scaling law, bits 1.5.
Right, the weight precision.
Yes, this represents the precision of the model's weights, basically how the neural network itself is stored in the device's memory. Whether the model is using precise 8-bit integers or highly compressed 3-bit integers acts as a massive amplifier for those k-vector errors.
How so?
Well, if a developer quantizes a model down to 3 bits to save space, and then introduces a tiny angular error into the key vector, that low-precision mathematical environment acts as an accelerant. It severely blows up the downstream perplexity penalty.
So it makes the error way worse.
Exactly. The exact same k-vector error run through an 8-bit model might barely register on the output quality.
Okay, so summarizing the implications of this scaling law is really vital for understanding the hardware design that follows.
Definitely.
We know the k-vector signal is highly concentrated in the low frequencies. We know that any errors introduced during compression will compound quadratically and destroy the model's output.
Yeah.
And we know that we can only survive those compounding errors if we're utilizing a massively parameterized model capable of averaging them out.
Right.
The profound challenge presented by the Shannon Prime researchers was taking these abstract, high-dimensional scaling laws and mapping them directly onto the physical constraints of silicon hardware.
And that is where things get really fascinating. So we have this fragile, highly concentrated signal, and we have the math telling us our margin for error. The incredible leap the researchers took was organizing this abstract math into physical storage tiers.
Right. They conceptualized the Vilenkin-Hartley spectrum through a framework they called multiplicative lattices,
Yes.
which relies on the properties of prime numbers to group the frequencies. And the naming convention they chose for these tiers beautifully translates the math into physical intuition. I love these names: granite, sand, and jazz.
There are great names. Multiplicative lattices offer a way to organize frequencies not just by their order, but by their fundamental divisibility and harmonic relationships. In this framework, granite corresponds to band 0 of the transformed K vector.
Band 0.
Right. This band is constructed from the fundamental primes that dictate the macrostructure of the sequence. It contains roughly 86% of the signal's total energy. Granite is dense, it is incredibly slow-changing, and it represents the absolute global positional relationships of the tokens.
It is the mathematical bedrock of the entire context window. Granite, the heavy, unmoving foundation.
Exactly.
Then, built on top of that foundational lattice, we have the second tier, sand.
Sand encompasses bands 1 and 2 of the transform spectrum. This is the mid-energy domain. The frequencies here represent regional geometry. The relationships between tokens within a specific paragraph or sentence rather than the entire document.
So it's more localized.
Very localized. It is granular, it is redistributable, and it provides the structural detail the attention mechanism requires when it needs to look closer at a specific spatial cluster. It acts as the shifting dunes resting on top of the granite bedrock.
Which leaves the final tier, jazz, band 3. This is the noise tail of the spectrum. It is low energy, highly contextual, and improvisational.
Jazz carries the finest, rarest mathematical textures.
Right. It represents the hyperlocal relationships between adjacent words. It is chaotic, high frequency, and entirely unpredictable.
And translating these granite, sand, and jazz lattices into a physical hardware architecture requires mapping those mathematical properties directly to the storage hierarchy of a device. Because granite contains 86% of the crucial spatial signal and is demanded for virtually every single attention calculation, the system mandates that granite be stored strictly in the fastest, most expensive storage tier available.
Which would be the device's primary working RAM.
Exactly. RAM. Now, sand, which carries less energy and is accessed less frequently, is pushed down the hierarchy to the fast local disk, specifically NVMe solid-state drives.
And jazz, carrying the lowest energy and the highest entropy, is banished entirely to cold storage.
Yep, cold storage.
The device only ever pays the massive physical latency cost to drag the jazz data off the cold disk if the granite in RAM and the sand on the NVMe drive completely fail to resolve the AI's attention query. It's an incredibly intuitive design.
It really is.
It builds a perfect bridge between the abstract topologies of Lincoln-Hartley math and the tangible silicon reality of RAM and solid-state storage.
But mapping the data conceptually is only half the battle. The physical roadblock is the execution. I mean, during a live generation, an AI model is predicting and outputting up to 20 words a second.
That's incredibly fast.
Right, and the attention mechanism needs to access this tiered data continuously. So the question is, how does a standard NVMe drive physically seek and fetch these disparate architectural tiers across gigabytes of storage without causing the entire generation process to stutter and stall?
Which brings us to the mechanical ingenuity of the system, the architecture of progressive loading. To keep the AI streaming tokens smoothly across these separate hardware components, the researchers designed a highly orchestrated three-phase process.
The three phases are critical.
Phase 1 is the core mathematical primitive, the in-memory partial dequantize. Let's break that down.
Sure. So in a traditional system, when a compressed vector is retrieved from memory, the CPU must unpack the entire vector, converting all the bits back into a format the processor can use. This bit unpacking loop consumes millions of clock cycles.
Just a massive waste of energy.
Huge waste. But the in-memory partial dequantize fundamentally alters this. Because the data is structured into bands, the processor is programmed to read only the specific bands requested, say, just the granite in band 0, and physically zero out the remainder of the vector directly in memory.
It's like receiving a massive zip file containing an entire library of books. In a standard system, the extraction software forces your computer to unzip every single file in the archive before you can read the one summary document you actually need.
Which takes forever.
Right, wasting enormous amounts of computational time and thermal energy. But the in-memory partial dequantize acts as an intelligent extractor. It reaches into the zip file, unzips only the specific granite folder you requested, and completely bypasses the computational costs of extracting the rest of the archive.
Exactly. The unread bands never even touch the bit unpacking loops of the CPU.
Okay, so that's phase 1. What about phase 2?
Phase 2 of the progressive loading architecture addresses the physical limitations of the storage drives themselves by introducing the band major V3 disk format. To understand the massive performance gain here, you really have to look at how data is physically arranged on a NAND flash memory page.
Okay.
In the older traditional interleaved formats, the storage drive placed all the data for token 1 sequentially, followed by all the data for token 2. So it would write token 1's granite, sand, and jazz, and then token 2's granite, sand, and jazz.
So it's interleaved. But if the attention mechanism decides it only needs to evaluate the granite tier for, say, the first 1,000 tokens, the hardware controller on the NVMe drive faces a physical nightmare, doesn't it?
Oh, an absolute nightmare.
It has to seek to the start of token 1, read the granite, skip over the sand and jazz, seek it to the start of token 2, read its granite, skip the rest, and basically repeat that process 1,000 times.
Yes.
It's like a record player needle constantly lifting and dropping to find specific lyrics across an entire album.
That's exactly what it's doing. And on modern NVMe drives, while the actual reading of data is incredibly fast, the physical act of seeking, locating the specific block of data on the flash memory costs roughly 50 to 100 microseconds per seek.
That adds up fast.
It does. Force the drive to execute thousands of random seeks per second, and the controller is overwhelmed. The IOPS, the input-output operations per second, just plummet, the latency spikes, and the AI stalls.
Right.
The band major V3 layout solves this by completely re-architecting the physical layout of the disk. It places all of the granite for every single token in the context window into one massive contiguous block of memory, then all the sand in the next contiguous block.
So when the system needs to evaluate the foundational granite across 50,000 tokens, the NVMe controller doesn't have to seek 50,000 times.
No, not at all.
It just finds the start of the granite block and performs a single massive sequential read. It basically just sweeps the needle across one unbroken groove.
And this is exactly where modern hardware shines. A PCIe 4.0 NVMe drive can pull sequential reads at speeds of 3 to 7 gigabytes per second. By arranging the physical data to match the mathematical bands, the system saturates the PCI bus, slurping up the entire granite tier in a fraction of a millisecond.
That is incredibly elegant. But streaming the data efficiently is useless if the system doesn't know when to stop reading.
Right.
Which leads to phase 3, which the documentation refers to as the brain of the operation. Entropy-gated short-circuiting.
Yes, the entropy gate. As the AI streams the granite from RAM and the sand from the NVMe drive, it is simultaneously computing its attention scores, calculating the probability distribution of which prior tokens matter most for the current prediction. Entropy gating is the mechanism that monitors the Shannon entropy, the mathematical measure of uncertainty within that evolving probability distribution.
So it is continuously evaluating its own statistical confidence. If the AI evaluates the granite tier, just the bedrock spatial relationships and the probability math strongly concentrates on a specific cluster of tokens, the Shannon entropy of the distribution drops to near zero. The AI is mathematically certain it has found the necessary context.
Right.
The moment that threshold is crossed, the entropy gate slams shut. The attention calculation is short-circuited. The cold storage drives holding the jazz tier are entirely ignored.
And this specific architectural choice often draws scrutiny regarding computational overhead.
Oh, really?
Because introducing an entropy calculation in the middle of a high-speed attention loop does require additional clock cycles from the processor. However, it is an exercise in the economy of scale.
How so?
Well, calculating the Shannon entropy on a highly concentrated, low-dimensional probability distribution residing in the ultra-fast L1 cache of the CPU takes an infinitesimally small amount of time. It is computationally trivial.
Right.
Conversely, forcing the system to unnecessarily wake up a cold solid-state drive, seek a block of jazz data, drag gigabytes of information across the motherboard bus, and unpack it through the processor that costs a relative eternity. The microscopic overhead of the entropy gate pays for itself thousands of times over by preventing catastrophic disk reads.
That makes total sense. So we have mapped the theoretical landscape. We have the concentrated Volink and Hartley signal, the scaling laws dictating our error margins, the multiplicative lattices grouping the granite, sand, and jazz tiers, and the three-phase progressive loading system sweeping contiguous blocks off the disk and slamming the entropy gate shut.
We've covered a lot of ground.
We really have.
Yeah.
But the ultimate test of this architecture is deploying it into the real world. So let's examine the hardware deep dive from the Shannon Prime documents, specifically the engineering challenge of putting a 50,000 token context window onto a consumer smartphone like the Samsung Galaxy S22 Ultra.
Right, mobile AI. The primary barrier for mobile AI is the strict limitation of physical RAM. If you attempt to run a 50,000 token context window using an unoptimized standard key value cache, the mathematical vectors balloon to roughly 2 gigabytes of active data.
Which is massive for a phone.
It's huge. On a high-end smartphone with 12 gigabytes of total system RAM, dedicating 2 gigabytes solely to the AI's memory cache creates a systemic crisis. The phone's processor is simultaneously trying to keep the operating system alive, manage background applications, and hold the massive neural network weights of the AI model itself in memory.
And when you force a 2 gigabyte cache into that constrained environment, the operating system basically panics.
Oh, totally.
It begins frantically paging memory in and out of the storage drive to keep the system afloat. The processor works in overdrive, the silicon gets physically hot, the thermal throttling kicks in to prevent the chip from melting, and eventually the system simply kills the AI application to save the phone.
It is a catastrophic hardware failure.
So how does progressive loading fix this?
Applying the progressive loading architecture fundamentally alters the physics of the device. By utilizing the banded quantization and the granite, sand, jazz tiers, the system guarantees that only the foundational granite working set must remain resident in the phone's primary RAM.
Just the granite.
Just the granite. Because granite consists only of band 0, it represents an incredibly dense mathematical compression. The total size of the granite data per token is squeezed down to approximately 22 bytes.
22 bytes per vector. That compression ratio is just staggering.
It really is.
When you multiply 22 bytes across the entire 50,000 token context window, the massive 2 gigabyte memory footprint collapses into a flat, highly manageable 30 megabytes.
Exactly, from 2 bigs to 30 megs.
And because of the entropy gating, that 30 megabyte footprint remains static regardless of how vast the conversation becomes. The sand and jazz tiers sit entirely dormant on the phone's UFS storage drive, consuming 0 power and 0 RAM, only waking up for a microsecond when the entropy gate demands deeper context.
Because the RAM is liberated, the thermal load drops, the phone runs perfectly cool.
But the memory reduction is only part of the mobile optimization, isn't it? The researchers specifically targeted the neural processor inside the Snapdragon system on chip, the Hexagon V69 NPU.
Yes, the Hexagon NPU. This processor represents a profound symbiosis between the mathematical software and the silicon hardware. The Hexagon NPU is built around a very long instruction word architecture, specifically utilizing pathways called HVX hexagon vector extensions.
HVX. What makes that so special?
The HVX pathways execute massive 124-bit vector instructions, allowing the processor to perform 128 individual 8-bit integer operations in a single clock cycle.
Wow, so it is just chewing through massive blocks of low-precision sand and granite data simultaneously, rather than processing them one number at a time.
Precisely. Furthermore, the NPU features specialized hardware tensor accelerators known as HMX matrix extensions. These are physically designed to execute 256 by 256 8-bit integer matrix multiplications. This specific hardware layout acts as a physical accelerator for the inverse Vilenkin-Hartley mathematical step. The silicon is physically wired to execute the exact mathematical transformations required to reconstruct the k-vectors from their prime harmonic bands.
That is incredible. And the coordination between the chips is equally critical. I mean, if the NPU is performing these massive matrix multiplications, but the main CPU is running the operating system, and the GPU is rendering the chat interface on the screen, moving the KV cache data between these discrete processors usually creates a crippling bottleneck, doesn't it?
Oh, a massive bottleneck. Dragging data back and forth across the motherboard bus destroys battery life.
Right.
But the hexagon architecture bypasses the motherboard bus entirely through tiered memory access. The system utilizes the Snapdragon's shared CPU-GPU cache fabric. The processors use a highly efficient stack and pop memory pattern.
Second paw.
Yeah. The CPU places the necessary tokens into the shared cache, the NPU pops them out, executes the HVX vector extensions, and places the resulting attention scores back into the cache for the GPU.
So there are absolutely no PCIe class round trips required.
None.
There are no redundant copies of the data created in the video RAM. The Hexagon NPU runs in total parallel execution with the CPU and GPU, accessing the fabric directly.
And by eliminating the data transit costs and utilizing the banded quantization, the entire AI memory operation draws approximately 500 milliwatts of power.
Half a watt to manage a 50,000 token context window? That is just It's hard to even wrap my head around.
The efficiency achieved here cannot be overstated. It feels less like executing software instructions and more like striking a tuning fork.
Ah,
The hardware, the specific 24-bit pathways of the hexagon NPU, acts as a physical resonator. It is perfectly, intrinsically tuned to the mathematical frequencies of the multiplicative lattices.
right.
The efficiency is a natural physical consequence of aligning the mathematical topology of the data with the microscopic geometry of the silicon.
So, we have journeyed through a monumental paradigm shift in computer science today. We started by discarding the rigid, binary storage locker metaphor for memory. We examined how the rope E-embedding structure, key vectors, allowing the Vilenkin-Hartley transform to concentrate 80% of the spatial energy into the first 20% of the frequency bands.
Right.
We explored the rigorous mathematics of the scaling laws, demonstrating how the quadratic compounding of attention errors can be safely absorbed by the massive parallel juries of 70 billion parameter models.
And we observed how those mathematical frequencies were organized by prime numbers into the granite, sand, and jazz tiers and mapped directly onto physical hardware.
Yes, and we detailed the engineering brilliance of the three-phase progressive loading system, utilizing in-memory zeroing, the sequential NVMT sweeps of the band major format, and the continuous mathematical confidence checks of the entropy gate.
We covered it all. And finally, we saw how executing this architecture on the HVX pathways of a hexagon NPU reduces a catastrophic 2 GB mobile bottleneck into a hyper-efficient 30 MB footprint, drawing only half a watt of power.
The ultimate implication of this invisible architecture is profound. The ability to manage massive KV caches locally on a consumer smartphone means that the era of relying on cloud servers for complex AI computation is ending.
It really is.
This infrastructure puts hyper-intelligent, context-aware AI assistants entirely on your local device. It guarantees absolute privacy because your data never leaves your phone. It guarantees zero latency because you are never waiting for a server response. It essentially transforms the smartphone in your pocket from a simple communication terminal into a sovereign, isolated supercomputer.
But, the Shannon Prime source material hints at an even more radical future, pushing the boundaries of what memory fundamentally is.
Oh.
If the foundational granite lattice is entirely dictated by the rigid mathematical frequencies of the model's weights, and if the specific zero crossings of that spectral signal can be topologically predicted using the properties of prime numbers, the logical conclusion is the complete elimination of the cache itself.
Wait, elimination, like completely.
Completely. If the math is entirely predictable, we eventually won't need to store the granite, sand, or jazz tiers on a physical disk or even in RAM. In the near future, the KV cache won't be data you retrieve from a memory module. It will be a pure mathematical function.
Wow.
The AI will evaluate the prime zero crossings on the fly, regenerating its own memory from scratch instantly across the attention heads without storing a single physical byte. It is the total conversion of historical context from static storage into dynamic computation. It changes everything about how machines perceive time and memory.
That is incredible to think about. Thank you for joining us in this deep dive. Keep questioning the invisible architecture of the tools you interact with every day because the most profound revolutions in technology are usually hiding right there in the math.